Now we come to the integral, which is the continuous version of a sum. The sum of all of these values will tell us whether this sine wave is necessary to build the square wave. If the sum is positive, the waves are overall correlated, and this sine wave is in a Fourier series of this square wave. If the sum is 0, the waves are not correlated at all, and none of this wave is used to make up the square wave. If the sum is negative, the waves are overall anti-correlated, which is kind of like grooving upside down, so the negative of the sine wave goes into the Fourier series. It turns out that the sum is positive, so sine 3x does indeed go into the making of this square wave. But how much of it? After normalization, we get a value of 1/3. This tells us that only 1/3 of the amplitude of sine 3x is used to make the square wave, and when we compare with our earlier example, we do indeed see the term 1/3 sine 3x. So to recap, the multiplication tells us how correlated the waves are at each time step, and the integral tells us how correlated the waves are overall. Now notice how the square wave is made up of only odd sine terms, and it's pretty easy to see why. For every period of the square wave, there are always 2 more correlation humps than anti-correlation humps. So the sum will always add to a positive number, whereas with even frequencies, the positive and negative humps exactly cancel out, leaving us with a sum of 0. This is also why we don't see any cosine waves in the series. The Fourier transform does this same process for any frequency, thereby telling us which frequencies go into any specific function.